Okay, can you hear me? Great. I've never worn one of these TED Talk microphones, so this is like totally new headgear experience. It's kind of awesome. All right. So yeah, I'm Todd Gamblin. I lead the Spack package manager team. Spack is a package manager for supercomputers, and so we grew up in the world of HPC, started in about 2013, and have gotten widespread use since then. We're trying to build for very large machines, and also for clouds and clusters and laptops, and even on Windows now. So we're really trying to build everywhere, but a lot of the environments that drive Spack development are ones like these. So Frontier's the #1 machine in the world right now. It's an exascale machine. It has 37,000 MI200 or MI250X GPUs. Sierra is a machine that we have at Livermore. It's got a bunch of, I think 17,000 V100s. So we're very concerned with running in, sort of exotic environments and lately with GPUs. We're trying to build things that have, lots of different languages mixed together: Python, Fortran, C, C++, some other things. And we want to allow arbitrarily many installs of basically any package. So we want people to be able to experiment to get performance out of their installation. Spack's it's inspired by Nix and Homebrew. And so if you look at the deployment model for Spack, it looks a lot like Nix. Everything goes in its own prefix. If you look at the package DSL for Spack, which we'll see a little bit in this talk, it looks a lot like Homebrew, but in Python. There's lots of users and around 7,400 packages at this point, so the ecosystem has gotten a lot more complicated than it was when we started. So we care about this because a lot of codes people write for scientific computing, they use a lot of open source, and that really increases the number of packages that you have to deal with. So this is Aries. It's a multi-physics code. It simulates things like fusion ignition and so on at Livermore. And a good 75% of this thing is open source, either developed at our lab or developed outside of it. And we want to be able to manage this stuff, but it's managed by other teams. And people need that to be flexible. There's really 3 parts of Spack, just to give you kind of an overview of what it does. There's a spec syntax that you can interact with it on the command line. And so for that, you might say Spack install some package. This just says, get me a version of that package. I don't care what it is, hopefully the latest. But I don't care about the rest of it. You can have control over that. You can say, I want a particular version. You can say, I want to build with a particular compiler. You can say plus threads if the package has a threads option. Different packages can expose different options, and they can depend on options on other packages. And you can inject flags into your build. You can target a particular microarchitecture, and all of that's recursive, so you can control all of those same things for your dependencies. This language drives the package files in Spack, and each package file, like I said, it looks like a Homebrew class. Everything is a Python class, and there's really 2 parts to this. This part down here is the build recipe. We're not going to spend a lot of time on that right now, but up here is the metadata. And it's a little different from the package managers you may be used to in that it's telling you all the versions that are available and all the options that you have on the package, not just like one spec to build one version of the package. And so with this thing, you could build 3 different versions with or without MPI, which is a message passing library, with or without OpenMP. Those are both sort of parallel programming models. And it depends on MPI conditionally. So everything in Spack is sort of optional. You can have an optional dependency. You can have a non-optional dependency. And so there's one on CMake right there. We depend on CMake at version 3.0 or higher for this thing. This stuff is useful for things like GPU support. And one of the reasons that we've sort of doubled down on solvers in Spack is to support the complexity that comes from supporting, say, 3 different GPU architectures. We had to support CUDA, ROCm, and SYCL for the Intel GPUs. And so this is the sort of CUDA package that's evolved in Spack. This is a very abbreviated version of it. But this is a sort of superclass that people extend when they want to write a GPU package. And we're able in here to say, CUDA can be enabled or disabled for the package. And so this variant says you can set it to true if you want CUDA to be enabled. If you do enable CUDA, you get a CUDA arch parameter, and that gets you a CUDA dependency as well. And so down here, we've encoded a bunch of stuff that people have to care about when they write CUDA packages that really has more to do with CUDA than it does to the package that's extending this thing. But it's important. So we care about things like, if I want to build for CUDA Arch 75, if I want to build for a certain compute capability, I need a certain version of CUDA that's at least at a particular version. And then down here, we're encoding things like the relationship between the CUDA dependency and the compiler version that we support. So we have rules like this encoded for different compiler versions. What this is really mapping to is the language support underneath the compiler. So different versions of CUDA have different C++ levels. And so you need to make sure that the compiler and the CUDA version match up. So we would not be able to do all this without a fairly sophisticated solver. And we have sort of, the solver in Spack is called the concretizer. It takes an abstract spec for a package like the ones I showed before and turns it into a concrete spec, which is a fully specified thing that you can build. And so it takes a lot of metadata from different places. There's all of the commits coming in from contributors that go into our repository of these package files. And then there's also preferences in either your dev environment or on the command line that all get sort of dumped into this solve that says, find me something that satisfies all these constraints and spits out a graph at the end. And this thing gets stored in a lock file so that you can reproduce it later. But it's pretty flexible how you can take a stack, change a parameter, and have a very different stack for, say, a different architecture. You could take a CUDA stack, turn off CUDA, enable ROCm, and have an AMD GPU build of things if we wrote the packages right. So this is obviously NP hard. And this is what I'm going to talk about, is how to make this stuff go fast, or at least the things that we've done to make these types of solves go fast. Just for reference, Spack does install like Nix does. We hash this whole graph. We install everything in its own directory. And we do some crazy RPath things to make sure that that works. And we'll talk about this a little bit later, but the structure of Spack is basically, so Kat was talking about how one of the things that you have to care about is network operations. We don't care as much about that because like Nix or Homebrew, we have the whole package repo locally. So we basically have all 7,400 package recipes locally in the thing that you have checked out. So you can get full metadata for your solve. So the concretizer in Spack is implemented using something called answer set programming. And answer set programming, we like it because it is higher level than straight up SAT. And why is that? It's because it looks like Prolog, but it gets converted to SAT with optimization. I guess I didn't look at the animations on this slide. This is sort of a crash course in ASP, but there are these facts that describe the graph. So this here says there's two nodes, lamps and CUDA. One depends on the other. These are sort of, the meaning of these is really dependent on how you encode your problem. And so we've encoded them this way. But this describes a graph. And you can have rules that have variables in them that basically match on what facts are available. So this one says, hey, if you have a node called package that depends on package dependency, then you can derive the dependency node from that. So if you have these two facts in your problem, you end up deriving that MPI is a node in the graph. And it's called a ground rule when you don't have the variables in it. So that's what ASP looks like. Essentially, what the solver does is it takes that first order program with variables in it with sort of readable rules that are very general, and it takes them, like, so here you've got 4 dependencies and this rule. It takes that and it does something called grounding it, which basically converts all the variables. It instantiates this rule for every combination of the available facts. And so you get something that looks like this, that's sort of an exploded version of the first program. Where you have things that don't have variables in them, and then you can go and solve that in a SAT solver or basically a CDCL solver on the back end. And what you get out are not, it's not like Prolog where you say, hey, is this true or not? You get what's called a stable model out, which is basically a solution. And so you get, you can enumerate all the solutions. You can say, get me the best solution according to some optimization criteria, and so on. And we're using Klingo in Spack to do this. So that's sort of a very, very quick crash course in ASP. For problem sizes, the problems in Spack get pretty large, mainly because we do have to consider all of the dependencies for the packages that we're dealing with. And so this is sort of different from how pip might want to do things, because it does have to do those network operations. But the main logic program in Spack is about 250 rules. It's like 1,000 lines of code. And there's 20 optimization criteria in there that are trying to pick sort of the best solution. And problem instances can vary quite a bit. So like if you look at like GNU config that doesn't like require any compilation or building or anything, it's just one thing and it's got 150 facts and that's it. And you basically just reconstitute the graph from those and you're done. For progressively more complicated packages, I mean, we can get up to sort of 820 possible dependencies for something like ExoWind, which is a wind farm simulation, and 322,000 facts in the program. And so that's pretty big. And if you think that those 250 rules are going to get exploded for all of those facts, it's even bigger when you end up at the sort of SAT phase. And so to solve something like this, what we're doing is in Python, we're computing all the possible dependencies, which is why that's important. We're loading each dependency package.py to get metadata, and we're translating that metadata from these specs that are in the packages, like you saw, to facts in ASP. And then we're running this answer set program with the problem instance, and we rebuild a graph from what we get back. The slow parts are really the I/O that we do to load all the package.py files, and then the solve itself. So we're going to talk about how we've done some optimizations for that. One of the things that we've done most recently with the solve, and I presented at the last PackagingCon on the solver itself, so I'm not going to cover the basics, but the original model in Spack was that for any given solve, right, you have to have one version of every package in that solve. And that's a little bit constraining because things like the Python ecosystem have evolved to the point where every package really wants to over-constrain its build dependencies. Every package wants a different version of setup tools or a different version of something or other. And so if we try to solve GPTune, the version of PyGEvent here gets held back because NumPy requires an older version of PyCython, and GEvent won't work with that older version of PyCython. Or Cython, I guess. Like we prefix all the Python packages with Py. And that's not great because it makes it really hard for the package maintainers to come up with solvable package configurations when we port stuff over from PyPI's constraints. And B, it's not really as the developers intended it because we had to do something slightly different than what they did in CI. And so what we've done is we've added dependency splitting to the Spack solve. So we've added sort of another dimension of combinatorialness to our solver. And what it allows is for not this stuff up here, because this stuff is sort of in the runtime graph of GPTune. This is stuff that has to be available, and there has to be one of every one of those because they're going to get loaded either by the Python module system or by the C module system, and you have constraints there that really prevent you from ever having more than one version of a dependency. But for the build dependencies, where each of these two packages has a different build environment, we can use different versions of PyCython down here. And so what we had to introduce to the solve was this unification set idea, which is basically that there are different pieces of your solve that need to be kept consistent, or that need to be unified, where you have one version of each package within that circle. But outside of it, you can have version variation. And so this is not trivial to do in a SAT solver because I think most of the implementations of solvers that do this are really focused on that sort of one version per package constraint. And so we had to essentially take rules that look like this, where like if a dependency holds, then we derive a node for that particular dependency. And we do that by name, to rules that look like this, where we say if the dependency holds, we can have exactly one out of this set, which is basically the nodes, a dependency on a node with an ID. And so essentially we took a name up here and we converted it to this node tuple that has a name and a numerical ID that says which unification set is it in, or which duplicate is it of that package. And so we had to rewrite essentially a large chunk of the logic program to understand this and to understand there may be multiple versions of particular packages. One consequence of this is that you do have to have a max number of duplicates for each package, otherwise your solve gets unbounded and it will generate and explode forever. And so we dynamically set the number of dupes that we allow per package in the solve. And we had to refactor the way that we express package metadata in the solver. So these are package facts. This says that also lib has a particular declared version that came from the package.py. We had to wrap these in this package fact thing so we could write rules that would allow them to apply basically to, we can use these same package rules for also lib for any duplicate of also lib, essentially. So we had to generify that. So we tried that, and the first time we ran this with the new rules, it was about 50%. It was 2x slower in some cases, and so it's quite a bit slower than our normal solves, which are actually getting pretty slow in a lot of cases themselves. And so this is showing the total time for grounding and solving. And for some packages, it's running close to 30 seconds to begin with, and it's over a minute for some of these solves after that. And for an interactive tool, you really don't want this. You want the solve to go faster than that, because users will get frustrated with wait times of a minute. And so one of the things we found is that the cycle detection we were doing in the solve is actually quite expensive. So we have rules that look like this, where you say there's a path from A to B if A depends on B. There's a path from A to C if A depends on B and B depends on C, and so on. So this is transitivity. You can basically say no cycles by saying disallow that. The problem with this is that it requires the solver to maintain all the paths that exist between any set of nodes in your solve. And so that gets quite expensive when you end up doing the solve, because it has to explore all of those, maintain them, and basically generate them while it's doing the solve. So taking this out got us a 50% improvement in solve time. So we're already kind of back to being close to where we were before. It turns out that unification sets themselves can be expensive because they're recursive also. So in our first implementation of this, we just said, okay, if you have something in the run graph, don't put a unification set around that whole thing. But if something's a build dependency, give it its own unification set. And so we let those things basically recursively propagate out through the dependency DAG. What that does, though, is it causes your solve to explode again. And so we basically, we came up with heuristics for saying which things could be duplicated. And we basically said, if you're not in that set of things, we're going to dump all of your dupes into one unification set. And so you only get one chunk of the graph. Coming up with better heuristics for this is something that we'd like to do later. But you put all that together, and essentially you can see here that these blue lines these are different packages down here, and this is the amount of time we're taking to solve them. The blue lines are the first implementation. The orange is the optimized cycle detection. The green is optimized unification sets, and the red is another optimized thing that we did that's similar to the paths. And we were able to get 10x or more improvement over the initial implementation in many of these cases. And so that was pretty cool. This is a lot of work that it took to implement a fairly simple conceptually feature in the solve, because we sort of had to reformulate the whole model to do this. And we tried other models before we did this. We tried to make the solve iterative, where we would basically solve a build environment separately from a run environment. But it doesn't work, at least for us, because we want to be able to model relationships between the build and the run environment. So if you think about, say, setup tools. Setup tools, if you use it, it's injecting code into the thing it builds. And so you have a constraint that the setup tools in your build environment has to use a Python that it matches the version of Python in the run environment. Otherwise, the injected code can't be executed. And so there's a lot of things like that, and even more than that for cross-compilation, that we want to be able to model in a coupled way between the build environments and the run environments. And so we had to strike this, because to get those relationships, we were starting to have to ask the packagers to annotate their dependencies with things like this. And it just got to be impractical. It's not something anybody wants to think about. So we wanted that to be automated. All right, so that's the solver optimizations and the sorts of things that we have to think about for making ASP programs work well. The other bottleneck is really that I/O in the loading of all the packages. And so if you look at these two graphs, this is an M2 Mac, and for some reason M2s are like blazing fast at doing ASP solves. The bandwidth on the thing really does well for SAT. And this is a Cascade Lake cluster with an NFS home directory. And you really pay a price there. A, the Intel chip is slower at doing the ASP solves, and B, NFS just really sucks for loading lots of files. And so anything that you do on the NFS cluster, you have to be very careful about the metadata operations that you do on the file system. And so we tried to think about how we could make this thing faster. One thing you can do is parallelize loading. And so 5 to 10x improvement seems possible there if we were to do that. We haven't done it yet. But you'll eventually saturate the file system bandwidth. So is there anything else you can get out of this? The other thing that we can actually do is cache the metadata from the package.py files. And that is tricky because in the Spack DSL, it's pure Python, right? And so you have things that are pure Python code that you might execute that you really can't cache because they might be like fetching something from the environment. We would like to disallow that in our packages, but some people use this locally. They want to do bad things locally. We don't want to disallow them from doing that in their own home. And so we looked through the package.py files to see what we would have to do to get something cacheable. And so these variant directives here are mostly constant because they have mostly string inputs. But some of these methods, like will go and detect the network on the system to tweak a default for that particular system. It doesn't violate reproducibility really because this gets dumped in a lock file, but it just means that you're doing detection at class instantiation time. And then down here, we have references to other packages. So Boost exports some constants that say, here are the default variant sets and things like that. We don't know that they're constant just from looking at the AST here. So it's not obviously something that we can cache unless we work real hard at analyzing the package files. So we looked over all the packages and made an AST analyzer to see how much of these things we could cache. It actually turns out that most of the packages are all constant. And so something like 7,000 out of 7,400 packages just have all constant values in the directives, which is all this green stuff here. And 494 are not constant right now, but if we worked a little harder, I think we could get it down to just this red sliver that is sort of non-constant, where we would have to load the package files. So for a typical solve like HDF5, that eliminates like 85% of the loads that we would have to do at the start of solving. And so we could really reduce the metadata operations there by like loading a single JSON cache instead of loading all these Python files. So I think this is going to happen. This hasn't happened yet, but this is why we think it will help. So anyway, those are ways to make solves fast. I think we're on the path to faster solves in Spack. The multiple dependency stuff, the duplicates is already merged. So I think we'll be able to handle the Python ecosystem better and eventually have better support for compilers as dependencies. And the main bottleneck left for the solver, or at least I think at this point, is the setup. So essentially loading all those Python files. So we're working on that. So it's tricky, but it's not intractable. You have to jump through some hoops, but you can get fast solves, and I think every time we add a new feature that costs something, if we go and wring more performance out of the solver, I hope we can keep doing that until we can't anymore, at least. So for now, we're breaking even with the optimizations versus the features. So thanks. Any questions?
Hello, thanks for your talk. I used to use Debian stuff. I used to fight with the dependency resolver. I haven't been doing that for years now. I've been kind of dependency solve free, and I'm, I guess, not looking back. Nix, I think, doesn't use dependency resolution, really.
That's true.
So why did you, when you started Spack, decide to go, like, it's really impressive, I guess, some of the stuff you described, but why did you decide to do this to yourself in a way?
We wanted more flexibility, right? I mean, like, so with Nix, like, you can do an overlay, right? Like, you can have like your functional package, and you can say, I want something slightly different from that. Here's some Nix code to overlay. But there's no check on that says, oh, the overlay that you just put there is now incompatible with 6 things in your dependency graph, right? You have to find that out the hard way. And so what we really want here is a system that can do builds that you haven't done before, right? Not just one that can reproduce builds that you've already done, but something where if I move to a new machine, like the 6 that I showed on the first slide, that I can very likely take what I already have in the package files and port it to a new platform quickly, right? And by changing a few parameters. And so really what we're trying to do with the solver is make it do all the distro curation work that people have to do when they hack on like Nix packages, right? And it's helpful for things like, so here's an example. We have CI, we have about 4,600 packages building there, and Intel wanted to work with us to have a one API stack that built with their one API compilers. We changed one variable, right? And the whole stack re-resolved with different versions and different things, and we built most of it with one API right out of the box. And so it makes things like porting a very large software stack easier, and I mean, that's why. The solver is really, it is doing work for you, right?
Maybe a short follow-up question on that. Has the solver, which can be complicated and a bit daunting, especially if it doesn't do what you want it to. Has that scared people away from Spack, you think, or?
I'm sure that it has scared some people away from Spack when I mean, there is a learning curve, right? I mean, although, like, from a user perspective, you say Spack install, it goes and does the solve, and it gives you, a resolution and a spec. It tells you what it did. So it's not that steep of a learning curve. But yeah, I mean, so people do get daunted by having to tweak components. But I don't think it's that much more complicated than like struggling with any build, right? People get daunted by builds all the time because they're the worst thing in the whole universe. And so, there's a whole lot of institutional knowledge that you need to port things to exotic platforms already. Like, I don't know, and maybe like just people in the HPC world have a higher tolerance for complexity in general. Like, they don't know what they're missing. Greg's going to talk about that in the next session. Cool.
So you mentioned that you moved cycles out of the dependency resolution to speed things up, cycle detection, sorry. Mm-hmm. So I'm kind of wondering, if you don't care about cycles during resolution, why do you care about detecting them at all?
So I did a bad job of explaining that because I did have it on the slide. We did not take out cycle detection altogether. We took it out of the solve. And so now what we're doing is we solve, and cycles are very rare in solutions. And so we do a post check on what we get out, which you can do in linear time and just traverse the graph. And then if there is a cycle, we go and run it again with cycle detection. So we're only paying the cost for the things that actually have cycles, which is very few packages. We learned at the University of Potsdam yesterday, they developed this Klingo solver, that there's like some kind of built-in cycle detection that we might be able to use in the C++ level. And so we may yet put cycle detection back in and not have to pay the cost for those few packages. So yeah, we do care about it.
Okay, unfortunately no more questions. We're running a little bit behind, but there is a couple of questions in Discord as well.
Okay, awesome.
So yeah, thank you, Todd.
All right, thanks.